Okay, welcome to note set number 6, which concerns itself mostly with, well, completely with sinusoidal ideas. So we'll see quite a few things in this. This one will be a little longer video than the other ones, but couldn't really see how to slice it up any finer. I suppose I could have, but we'll see. Okay, so sinusoid, we've got could be with a sine or a cosine, but it's basically got three things. We've got amplitude A out in front. We've got frequency, omega 0. We're going to be dealing a lot with radians per second, although we'll talk about hertz, but this is in radians per second, so you need to keep track of your units. It's no different than keeping track of units of length like feet or meters. So the frequency has to do with how fast this thing wiggles, as we'll see. And then phase in radians, not in degrees. And the reason that we need it in radians, we've got radians per second for omega times second for time. So this quantity is in radians, so we have to add radians to it. Yes, I know you'll see books that will put that in 57 degrees, omega 0 t, 377 t plus 57 degrees. That's just wrong, 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 wrong. It's worse than adding apples and oranges. At least adding apples and oranges, you end up with some amount of fruit. Okay, so make sure you keep all that straight. So here's a picture of a sinusoid. Amplitude A is obvious what it does. The frequency is related to the period, capital T, and we'll see shortly explicitly how those are related. And this quantity T sub 0, which is a time shift, is related to the phase. So in the next couple slides, we'll take a look at how those things relate to each other. So first, the relationship between the period and frequency. So if t is the period, that means that that's how long in time it takes for the sine wave to go through one cycle. So one cycle is 2 pi radians. If we think about time going from 0 to capital T, we have to have covered 2 pi. So here we are taking the argument at capital T. Here's the argument at 0. So looking at that difference, that's the total change in angle. The phi values end up canceling out, and we're left with the result omega 0 times capital T. That's an angle, right? It's radians per second times second, so it's in radians. And that angle has to be equal to 2 pi because that's one complete cycle. So right there it tells us the relationship. The product of omega 0 times capital T must be equal to 2 pi. But more importantly, we can then take and solve that for t, and we get this result, or we can solve it for omega 0 and get this result. So bottom line, 2 pi is always on the top, and you put the other one in the bottom to get the remaining one. So omega 0 in the bottom, you get period. Period in the bottom, you get the frequency. And you can always check with units to make sure that it works. We've got 2 pi radians over seconds, so that's got to be radians per second. Okay, good. Now the relationship between the phase and the time shift is a little bit different. We can explore that here. Now the phase shows up explicitly in the equation, but not in the picture, and the time shift shows up implicitly in the equation, but explicitly in the plot. So let's take a look at that. So we can write the time shift of a function by replacing t by t plus t0. Notice we define t0 as being a shift to the left. So positive t0 with a positive sign there gives us that shift to the left. So start with this unshifted sign and make that change. And so we've plugged in the t plus t0 there. And then we pass the omega 0 through, and we see that we get a term that looks like this. So if we look at that, we see our standard form, omega 0 t, going up to the top there, plus this quantity. So that quantity there must be the phase phi. So phi is equal to omega 0 times t sub 0. So it's proportionality, but what that means is that for a higher frequency, if omega 0, come on, go away there. There we go. If omega 0 is higher, that means for a given time shift, we get a larger phase shift. That's all that means. Now, this relationship is important in the lab. We'll see that a lot of our work here revolves around looking at phases, but when you take things into the lab and you're using an oscilloscope, and scope is short for oscilloscope, you can measure the time shift directly, but you need to use this math to convert it into the equivalent phase shift. Okay, a lot of what we're seeing here is just standard unit conversion. So, if you can convert dollars to euros, when you go to over to Europe to have a good vacation, you should be able to convert all these things. You just have to know the right conversion factor. So for frequency, we've got radian frequency, omega, and we've got cyclic frequency, which we usually use the symbol F. Now, we've been using a subscript sub-0. That's just to our way of indicating a specific frequency, but we could leave that out. But we're going to get into scenarios where we're going to need both a specific frequency plus a variable frequency. And so we'll reserve the symbols without the subscript to represent a variable or a whole range. Okay, so radian frequency is in radians per second. Cyclic frequency is cycles per second, and then we have a special unit for that, which is called hertz. So one cycle is all the way around the circle. 2 pi radians is all the way around the circle. So we've got this conversion factor, 2 pi radians per cycle. If we use that, we find out that the conversion between omega and F, and I've missed the subscripts here. We could put them there. We don't need them. Either way, however we do it, if you got a frequency in hertz, you multiply it by 2 pi to get the corresponding frequency in radians per second. So that's all pretty straightforward. Now comes the fun part, complex valued sinusoidal time functions. So a lot of times, believe it or not, it's difficult to work with real valued sinusoids, and it's easier to work with their complex valued versions. I know you don't necessarily agree with me, but trust me, once you get the hang of working with these complex numbers, which are really not that hard, you've seen them over and over and over, and you should just nail it down here. We can write a cosine, a real valued cosine, as the sum of two different complex exponentials, e to the j blah. Blah is just a favorite phrase of mine that I use to describe a bunch of stuff that I don't want to say the whole thing. So this comes from something called Euler's formula, and it's basically just a relationship that says you take e to the j theta, that's a complex number, e to the minus j theta, that's a complex number, and here I'm showing them on the complex plane. So it's length of one, angle of theta for this one, angle of minus theta for that one. You then add them together, and you get this result. That's vector addition in the complex plane. And so you add them together, and that gives you 2 cosine theta. You can figure that out from trigonometry. You drop down a right angle here, and that's the cosine of that angle. So I should show that this angle here is theta. So from trigonometry we get that halfway out is cosine theta, double out, twice out is 2 cosine theta. and then that 2 ends up being moved down here, and we get Euler's formula. So this is a fundamental result. It will be crucial to everything we do from this point onward, so it's important that you learn that. Just think in this terms and you can visualize that. The key is to know that e to the j theta is a complex number on the complex plane, length of 1 because there's a 1 out in front, and an angle of theta. So you may be used to writing complex numbers as 1 at an angle of theta, or magnitude at an angle of theta, but really we need to be writing them as a e to the j theta. Now that becomes an actual mathematical result, an actual mathematical thing. It's a number. It works just like any other number. This is just a shorthand notation for that. Okay, so we can then find another form of Euler's formula by taking cosine theta here, j sine theta there, and we add them together and we get e to the j theta. So this is just doing some more trigonometry, and so here's two other forms. So what this is telling us, nice result, we can take a cosine and write it in terms of the sum of two complex exponentials, or we can take a complex exponential and write it in the form of a real cosine plus an imaginary sine. And also notice the negative sign here on the j becomes a negative sign there on the j. So everything works very nicely. Now, let's take a look at this a little bit further. This is just rewriting that form, but now instead of using a fixed angle, we have a time varying angle. So we have the time varying angle in there now. So perfectly good. So what that says is that as time goes on, since this is a plus j omega 0 t, it's going to be rotating in that direction. Angle is increasing. And a minus j omega 0 t term is rotating in the other direction. And as those rotate, they create the cosine that lies on this real axis. So as these things rotate, we'd start here and then this thing would shrink and then go in this direction and then come back, and it oscillates back and forth. And if you were to watch its values on that axis as a function of time, you'd see this cosine. And coming up, we've got some nice a link to some place where you can watch that. So there's a couple links here. There's one link there and there's another link here, and you can go and look at some web demos of those, and I would encourage you to do that. So why do we do this? Here's my attempt to try to convince you that it's useful to go into this complex domain, so to speak. If, on the other hand, you wish to solve your differential equations directly in terms of sines and cosines, be my guest. But trust me, it will be much, much, much harder. So this goes into the realm of phasors that you saw in circuits. You probably learned blindly how to use them, but may not have really captured why they work. So let's try to hit that here. So let's take a look at a simple RL circuit. We're going to apply a sinusoidal input voltage, which is given here by this cosine function. And now using Euler's formula, we can break that into this form. And then further, this is the beauty of writing complex numbers in this exponential form. We can apply properties of exponentials. A sum of exponents gives us a product with each term having one of the sum terms. So notice that what that does is it breaks the phase part out here by itself, and then we just have the part that oscillates there. And also notice that we have plus j, minus j, and minus j. So we have those two different parts. And I picked these numbers here for ease, not necessarily realistic component values. So now, we've got this sinusoid. We haven't, and we've recognized that we can split it into this form, but we haven't really done anything with that yet. But we're going to analyze this circuit. We're going to do KVL. So there is the KVL equation. And then we're going to substitute in our device rules, one for the resistor, one for the inductor. The inductor is where we get derivatives coming into it. When we substitute those in, we have a very nice differential equation that comes about from that. So we can try to solve that differential equation. Unfortunately, we have to solve it for this x of t being substituted in here. So we have to find some I of t that when we differentiate it, multiply by L, and don't differentiate it but multiply by R, that it equals this given x of t. So that's a little bit hard to figure out how to do that. But what we can do is we've broken the sinusoid down into a sum of two parts, so we can first solve for it when it's that, and second when it's that. Okay, so that's easy enough. So we sub in just the positive frequency term first. And so now we need to find, I have a subscript I sub p on that to just indicate that this is the positive frequency part of the solution. And we'd have to find the negative frequency part of the solution. And then by superposition, simply add those two things together. Okay, so what we need is an I of t that combines with a weighted version of its derivative to give an exponential. And so we know that exponentials differentiated give back exponentials. So it's really not surprising that we should expect the same kind of exponential function for I as we have for our forcing function. So that's the beauty here. Exponentials differentiated give just a scaled version of themselves. Sines and cosines flip-flop back and forth. Differentiate a sine, you get a cosine. Differentiate a cosine, you get a sine. And you can work it all out, but there's all these trig function identities and such. This just makes it easier to work it out. So we hypothesize, we guess that it's going to have this form, and then we say, well, okay, if that's the form, this is the derivative. You can just check that we're differentiating with respect to t, so our J100 comes out in front, as we would expect for differentiating a... man, this pen is just not working right here with erasing sometimes. So that makes sense, and we're going to hypothesize this, plug it in, and see what happens. So we plug it in, we plug in our solution, we plug this in for IP, we plug this in for its derivative, so they go in there. Here's the L value and the R value, here's the input, and then an interesting thing happens when we do that. So let's see what ends up happening here. We combine terms. So we've got a e to the j100t, e to the j100t, so both of those can get pulled out, and the stuff that's left is here. So now we see an interesting thing. We have an e to the j100t and an e to the j100t. So the thing that's in front of the left-hand e to the j100t must be equal to the thing that's in front of the one on the right side. So that's the condition for this hypothesized solution to really be a solution. So then we have to look to see, can we make that happen? In other words, can we choose an AP and a theta p to make that happen? And sure enough, if you set those things equal to each other and you do a little bit of complex arithmetic, complex algebra, you find that the resulting value that you need for AP e to the j theta ends up being this result. So here in the numerator we have something in polar form. Here in the denominator we have something in rectangular form. So we have polar over rectangular. It's easiest to divide things in rectangular form, or polar form rather. So we convert the denominator from rectangular form to polar form, and then it's easy to divide. The two magnitudes divide and the angles subtract. And so this is the complex number that represents this. AP is a real number, theta p is a real number, but the combination of those together like that is a complex number. Okay, so that tells us that we have solved for the positive frequency term. Now we do it for the quote-unquote negative frequency term, meaning we've got a negative j out there. This thing is rotating in the other direction, as we just saw. And you can do the same exact thing, and if you do that, you guess now with a negative j and a negative j, and we get the negative j out in front when we differentiate that. You plug it in, solve it just like before, and you get this. For the negative solution. And then we see that they are the same. The only difference is they are complex conjugates of each other. So now if we plug all that back in, we don't, well, what this tells us is we don't even really need to solve the negative frequency part. We can just guess. Once we have the positive frequency part, we know what the negative frequency part is going to be. You just negate the j and you get it. So that's really nice. So then we add them together, and again all we have to do is solve for one of those, solve for this part, and then we can immediately write this part. And then you just manipulate things together, you recombine the exponentials, so here they are combined, and now it's just Euler's formula all over again. This gives us Euler's formula. I specifically inserted a 2 there, doubling the 0.15 to give me the 0.030. And so now I have my cosine. And so that's exactly, well, let me say it this way. What phasors do is they take this whole sequence and trim it down to the bare essence of what we need to do. So this is really the rationale and the basis for doing phasor analysis. So let's redo it. Well, I'm suggesting that you try doing this directly with cosine. You would be doing pages and pages of trig identities, and I guarantee you'll make a mistake somewhere along the way. But more importantly, this idea tells us that we can trim away a lot of the excess stuff that doesn't really need to be done because it's superfluous stuff. Once we have the essence of what we need to do, we can use this phasor idea to quickly get the answer. So let's redo it. So this idea of phasors that seems so confusing in circuits class is really the simplest thing in the world. It's a series of steps that captures essentially what we just did. It's how to solve differential equations, circuits really, RLC circuits, but differential equations. It's a way to solve them quickly when our input is sinusoidal. So the idea is you take your sinusoidal function and you convert it into the phasor version. All you have to do is take the amplitude and the phase. We just saw that the e to the j 100t part just drops out. It's not important. It's extra baggage. So this captures the important components that we need. And then the other thing is we just convert our impedances, our inductor, into the equivalent impedance, j omega 0 L. And if we work back on that, we see where that came from, right? We can sort of see where that comes from. We get a j omega. Let me go back one more here to the previous page. We get the j omega from the differentiation, and then that term gets multiplied by an L. So there's the j omega L that comes for the impedances. So this idea is just a shortcut that simplifies all of that. So now all we have to do is we're trying to find the current. So in this case, we just have to find this total impedance. They're in series in this case, so it's just the sum of them. So 10 plus j200 is our complex impedance for that series. And then we divide our voltage by the impedance. And so we saw this showing up, something very much like that already. And so here is our phasor, our output phasor, the current. And this is just applying Ohm's law. And then we convert back from phasor to sinusoid. So we take the magnitude of the complex number as the amplitude of the sinusoid. We take the thing multiplied by the j, carrying along any algebraic sign, negative, positive, as necessary. And we reinsert our known frequency. And that's all we have to do. And so there it is, convert it to a sinusoid. Now we've done this here for a cosine. You can do it for a sine. If you start with a sine, you do everything the same, you just end up with a sine at the end. Okay, so that's the beauty of this, and really you need to make sure that you can operate with complex numbers. They are the bread and butter of this course, really. So some big ideas that we've seen here. Euler's formula, big thing that allows us to connect back and forth between these ideas. Excuse my pun here about making things more, seeming to make things more complex, but these complex sinusoids really help us out a lot, and we'll see that over and over. And what it does is it allows us a very easy way to solve a differential equation in general, or an RLC circuit in specific. Okay, so that's the end of that idea. Moving on to a totally different idea. We've looked at continuous time sinusoids. We've looked at discrete time sinusoids. Now, what happens if I take into this stream of systems that we've been talking about, we put a sinusoid into our A to D converter? We're going to get some discrete time samples, just a stream of numbers, but the question is, what are those going to look like? Well, they'll look like a discrete time sinusoid, no surprise. But the question that we really want to answer here is, how closely should these samples be spaced in order for us to have a workable representation of the actual sinusoid? So the ADC clock sets the sampling rate, which then sets the spacing of the samples. So at first thought, you might think that, well, you should take enough samples to make the discrete time sinusoid look like the original, but it turns out that in many cases that's excessive sometimes, and we want to minimize the amount of data we've got to store and process and so forth. So we want to find just how fast we need to sample and have everything still work mathematically. So here's a question for you. Here's some samples. What does your eye see? What sinusoid did these come from? Well, your eye says, okay, I see a sinusoid that looks like that. Okay, good. But here's the weird thing. Well, clearly they could have come from that one. Here's the weird one. Notice the red? I'm taking samples of that red one just as well as I'm taking samples of that blue one. So the question is, given these samples up here, how do I know which of these it came from? And in fact, I could find additional sinusoids that are higher frequency than the red one that are also satisfy these samples. So the thing is that from a set of samples of sinusoid, there are infinitely many different sinusoids that it could have come from. What we do is we say, all right, we're going to assume that it was the lowest frequency of all those possible sinusoids. So this is something we want to explore a little bit more. So if we want to be able to tell these two sinusoids apart, we would need to sample faster, or equivalently, if we sampled at this rate, we would have to at least assume that somehow we've limited the frequencies that we're allowed to sample to just be below a certain level. So we'll let T sub s be the spacing between samples. And remember, the reciprocal of that is called the sampling rate, and that's in samples per second. So if we take a continuous time sinusoid and we sample it, we get this quantity here, which we can define. That little square there should be a defined symbol, not a square. We can define that to be this discrete time frequency omega sub 0, and then we get something that looks like this. So again, that should be a defined symbol. I'll try to make sure it comes out properly in the posted notes. So the units of this thing are radians per sample, and it's related to the original frequency in hertz and our sampling rate according to that equation. So let's try to visualize this, what this discrete time sinusoid looks like. Remember, this omega sub 0 is telling us how many radians things move from one sample to the next. So these dots here are showing where this signal's complex components would fall. So we've got a positive frequency part and we've got a negative frequency part. So starting at n equal to 0, they both would start here, and then one moves this way and one moves that way. And at each click of the index n, they move, in this example, pi over 8. So that's a nice way to visualize this. So let's take a look at this as for the case of omega 0 being 7 pi over 8 versus omega 0 being 9 pi over 8. So the 7 pi is going to be on the top part of this plot, and the case for 9 pi over 8 will be on the bottom. And we'll walk through a few indices, a few sample numbers. So here's n equal to 1. So remember, they both started here, and then in one sample the top one goes 7/8 of pi, so it goes around to there. But the bottom one goes 9/8 of pi, so that's a little bit more than pi. So it goes past pi and a little bit more. Okay, so that's what we're looking at. So you'll notice that in the top we've got the red one up here. Down here the red one is on the bottom because it's gone a little bit farther. But remember, we're tying this back to a real valued sinusoid, so these two things get added together. The red and blue get added together up here, and the red and blue get added together down here. But the adding together makes no distinction between whether red's on top or blue's on top, right? So those two results are identical from the point of view of the real valued sinusoid underlying. Now let's see what happens when we go to n equal to 2. Now they each jump. So this one jumps from here over to here to give us that, and the blue one jumps from there over to there to give us that. But this one jumps, red one goes all the way over to here, blue one goes all the way over to here. So again, we have the same scenario, but again, blue and red, blue's on top and red's on top. But when we add them together to get the real valued sinusoid, it's exactly the same. And if we continue this on, we'll see that they're always in that situation. Always. So what that tells us is that a discrete time frequency of 7 pi over 8 looks exactly like a discrete time frequency of 9 pi over 8. And this is what's known as aliasing. Two different sinusoids look like the same thing. So one visual thing has two different names, essentially. The same sinusoid can be said to be a 7 pi over 8 frequency or a 9 pi over 8. So it's like it has two names. That's why it's called aliasing. And that's a key idea. So if we trace all this back to avoid aliasing when we sample a continuous time sinusoid, we want to make sure that the frequency of the sinusoid that we're sampling is less than Fs over 2. So this can be proved from the steps that we just went through, although we didn't go through all the proof steps, but we did motivate it. So what that means is that omega 0 must be less than pi. If we pick an omega 0 above pi, then we're getting another equivalent frequency. So we will always try to make sure that if we're sampling a continuous time sinusoid, the frequency of the sinusoid is less than fs over 2. And we'll always keep our discrete time frequencies less than pi. Now remember, we talk about positive and negative frequencies when we start talking about these complex components. So we're going to be talking about discrete time frequencies ranging between plus and minus pi. So for proper sampling, what this is telling us is that the highest frequency that we want, that we need to sample fs, our sampling rate fs has to be twice that, right? That's telling us that fs has to be greater than 2f0. Remember that CD sampling example I gave a few lectures ago, where I said highest frequency we can hear is 20 kilohertz. CDs are sampled at a little bit more than double that. This is where that comes from. Okay, so nice. So yeah, that's just summing that up there. And thanks for listening, and we'll see you on the next video.